All right, we'll see how I do with a microphone. I talk so loud that normally they don't let me use one. While we pull up the slides, I'll go ahead and introduce myself. My name is Chris Verlinden. The program says I'm the CEO of Applied Ocean Sciences. I wouldn't have corrected you, but our actual CEO is in the room. So Kevin, if you want to raise your hand. I'm the CTO and co-founder of AOS. We also have our COO, Alicia, if you want to raise your hand. She's our adult supervision. We also brought a couple of engineers, a data scientist, Evan, and Julian, I'll say our most tenacious electrical engineer. And I mean that because he's the one who is leading this particular project. And it absolutely does take tenacity, being stubborn, maybe a little bit nuts to try to develop technology in the ocean. And there's a reason for that. And I'm really glad, Tim, that you talked a little bit about the space world and the space ecosystem, because I think it's a good example and it's a good lead into what we're doing now in ocean tech space. And there's also some valuable comparisons to be made. So, a while back in the space industry, we got the memo that CubeSats were good. So having 1,000 toasters that can measure something okay is better than having, $1 trillion school bus that can measure one thing in one place very, very well. And so that memo, for some reason, took about 20 years to sink in the ocean world. Having lots of low-cost, compact sensors that can make measurements that are pretty darn good all over the world is incredibly beneficial. And we just got that memo in the last 5 to 10 years. I don't know, when basically you guys were founded. So that paradigm is happening. I think 5 years ago, I was saying there's going to be 2 orders of magnitude more sensors in the ocean in 5 years than there are now. That came true, and I think that's true today as well. I think there's going to be 2 orders of magnitude more sensors in the ocean in 5 years than there are today. The problem is developing ocean technology is incredibly challenging. Going back to those space people, they really need to quit whining, right? Because to get a sensor in space, even like a manned platform in space, you're dealing with 1 atmosphere of pressure. It's adorable. Talk to me when you have 500 atmospheres of pressure. Okay, you got a little bit of radiation, boo-hoo. Any problem that can be solved with tinfoil isn't a real problem, okay? Talk to me when you're putting your sensors in an acid bath under 500 atmospheres of pressure, getting wrecked by millions of joules of energy that is trying to destroy everything you love. There's an expression amongst oceanographers that you don't put anything in the ocean that you can't afford to lose. If you can afford to lose a $500,000 instrument, this talk might not be for you. Because what we've been trying to do is develop extremely low cost, low power, versatile acoustic instruments that are good for just about any application. Toasters, not school buses. The problem is that that's super, super hard to do for reasons beyond the technical. I talked a little bit about the technical challenges. We joked a little bit about the space people, but the technical challenges actually aren't even the hardest part. The problem is in the ocean tech space that every ecosystem is closed, proprietary, and if let's say I want to make an acoustic sensor because I'm an acoustician and that's what I do. I don't want to make a dissolved oxygen sensor. I understood about half the words you said. But I would love to be able to have my sensor used by the same person who's using your dissolved oxygen sensor. The problem is in most ocean technology ecosystems, you have to create an entire ecosystem of your own with your own data acquisition system. Like God forbid you try to collect temperature with this sensor and dissolved oxygen with a sensor made by a different company and collect it on a data acquisition system made by a different company, much less than share that via a comms platform. Everything has to be custom, and it's incredibly challenging to get into the ocean technology space. If you have an idea for how to make an incredibly powerful or super low cost sensor, it is really, really hard for you to actually get started. So what Bristlemouth, the open standard, has done is just lower the barrier of entry to organizations like ours that I think we have some good ideas, but we can't create a whole ecosystem. So now we don't have to. The sensor I'm gonna be talking about here today is called Borealis. That is an acronym. Doesn't really matter what it stands for. It stands for I wanted it to be a cool word. But the goal of Borealis is to do passive acoustic monitoring. We've had spoilers over the course of the day about why acoustics is important. Acoustics essentially is how we see the ocean. The ocean is challenging to work in because it's vast, it's highly dynamic. So when you take a measurement, it's not good in between a minute and an hour, depending on where you're working. And it's opaque to most standard sensing and communication media. Most frequencies of light don't travel very far underwater. RF, again, depends on the system a little bit, doesn't travel very far underwater. So if you want to see, if you want to talk, if you want to communicate, if you want to sense, if you want to navigate, for the large part, you're using acoustics. The problem is that existing systems are too expensive, too delicate. They take way too much power. They're difficult to use and integrate with existing infrastructure and ecosystems. They don't have sufficient endurance because working in the ocean is expensive, depending on the size of your boat, 20 to 150 grand a day. So going out and revisiting to change the batteries is something that can be untenable. And it's very, very difficult to implement your own edge processing on any existing system. And what I mean by that is, at Applied Ocean Sciences, we're very, very good at certain types of signal processing. A lot of our background is in the defense space, but we might not have the best classifiers for right whales or humpback whales. And that might be what you're trying to measure, but you have a good classifier for that. Well, you can run it on this platform. Traditionally, on existing systems, that's very hard. So these closed proprietary sensor ecosystems propose a very significant barrier to entry to small businesses that are trying to innovate in the ocean technology space. What Bristlemouth allows us to do is not have to create our own entire ecosystem, our whole standard, just to create a single sensor or a single algorithm. And that's why AOS has been incredibly excited to be working with so far on this system. So this is Borealis. That's what it looks like. I've got a unit here. We officially launched the product about 4 minutes ago. The website is now live. You can order it. All you got to do is go online to our website, which I'll show you. You can just start buying them right now. Just everyone buy one right now, so you have something to remember today by. The instrument that you will be buying is not acrylic. It is aluminum. Sometimes the acrylic doesn't love long deployments, but this one's see-through, so it's pretty. So I will pass it around, and you can check it out. That's what the system looks like. It is a extremely low cost, low power data acquisition system and low power edge processor attached to the standard SOFAR moat interface to the rest of the Bristlemouth ecosystem, and the most vanilla Linux SBC you could possibly imagine, a Raspberry Pi 02W with a full and open SDK, so you can develop your own software to run at the edge on that Raspberry Pi. If you've ever touched a Raspberry Pi, you can run software on this instrument. And if you haven't touched a Raspberry Pi, you probably still can, because we provide templates and examples solving a few interesting problems, with examples, and we've defined the pipelines of data in, the messages out. All of that is well defined, so you can run your own stuff at the edge as well. The system's designed to be deployed with the spotter buoy. I put a lot of interesting graphics in the top right corner, just so you guys know. So that's just going to be blocked the entire time. No, it's okay. It's okay. It's designed to be deployed with the spotter buoy or with with anything else in the Bristlemouth ecosystem. You can also optionally attach temperature and salinity probes to it and pressure if you need to know that for whatever your monitoring solution is. So this is a schematic of the device. I probably should have had this slide up when I was telling you what was in it. So you'll recognize the standard Bristlemouth sockets here, and then a vent for charging with nitrogen if you want to, or pressure testing. You can see that there's 2 sets of Bristlemouth sockets. That's because this is designed to be used daisy chained, so you can attach multiple together and construct an array out of them, and then process it like an acoustic array to do things like direction finding, time difference of arrival, beam forming if you want to get aggressive, and attach a lot of them. The Linux SBC is on the back side here. This is the SOFAR moat. These AOS PCBs are sort of our secret sauce. That's where the low-powered processors live. And then there's a sort of comms and carrier board, and then this little SensorTech SQ17 hydrophone. If you guys haven't used SensorTech for your acoustic sensing needs, you're wrong. They provide all of our piezoelectrics for everything passive active that we do. They're an awesome company. This is the SQ17. I'm going to throw it to you so you can see that I don't care if I drop it, because I can't break it if I try. I've tried. Niru, are you in the room around here? Raise your hand if you want to talk about any SensorTech stuff. After using her equipment, I would never go anywhere else. This SQ17 is a workhorse. It's invincible. Like I said, I've tried to break it. It is very sensitive. You're probably not going to find a Seawolf submarine with one of these. And that's a good thing, because that means you can export them. And it's very sensitive across a very broad range. So it's an incredibly versatile piezoelectric element. And like I said, if you have your own data acquisition systems and everything, I would never go anywhere else after my experience with it. Here are the specifications. So on the right side, again, my super cool graphics always in the top right. This is a spectrogram. For those of you guys who are used to looking at acoustic data or just measurements of sound in water, it'll look familiar to you. But in this particular case, there's time on the y-axis and frequency on the x-axis. And then the color tells you how loud it is. It's the intensity of the sound. So red is loud and green is less loud and blue is very quiet. So these are measurements of a ship passing taken on a Borealis unit a couple of months ago. These striations are, really sort of the quintessential CPA, closest point of approach. So if a vessel passes, you get those sorts of patterns. It's really included to show you that it does, in fact, look like acoustic data, because it is. The receive sensitivity on the hydrophones is, just under -200 decibels. That means it is fairly sensitive, but not to the point where it's illegal. The working frequency of this hydrophone, like I said, it's got a darn near flat response curve between 1 hertz, super low for the seismic people, to 100 kilohertz for you marine mammal enthusiasts. The Borealis unit itself, the thing that makes it special is the open interfaces, its membership in the Borealis ecosystem, its extremely low power consumption, which gives it a very long endurance, the high quality acoustics, its versatility. So while it might not be the best system for sticking inside a volcano or the best system for finding a Seawolf submarine, under the right conditions, for the Seawolf it'd have to be inside, it can do just about anything. It's also disruptively affordable. We think you probably couldn't get just the hydrophone element that's that good for the cost of this entire instrument. The depth rating of the current system is 100 meters. That's not design depth. Every single component's designed for 950. I just don't have a very big pressure chamber in my garage. So that's a testing limit. We'll be increasing that limit once we've done it ourselves. And we can confidently say it'll withstand the pressure tests. The power consumption is 40 milliwatts. Most folks think that's a typo, because that's what we basically spent the last 5 years of our lives accomplishing. In that low power mode of 40 milliwatts, you're able to acquire data, save it on up to 2 channels. If you stuck an extra instrument on there, you're able to process it and do things like decade band energy levels, SEL, SPL. For those of you in the industry, you're able to do exception-based reporting and energy detection with specified user-defined bands, all with 40 milliwatts. The maximum storage is it's a 1 terabyte card, which gives you easily over 60 days at the highest sample frequencies. The default sample frequency is just over 30 kilosamples per second, can easily be adjusted to 60 and less easily adjusted to 100. The bit depth, for those of you guys who do acoustic recordings, is 24 bits dithered to 16. It means your functional bits is somewhere in between. What that really does give you is a pretty impressive amount of both dynamic range and resolution. So you can hear a pile driving operation without clipping, and at the same time have the sensitivity to hear something very quiet as well. So we're also very proud of those statistics. We designed this, like I said, for versatility. We designed this hydrophone to be good for just about any acoustic application. Specifically, many of the folks we're talking to as users today are in the marine mammal community, environmental impact awareness, or assessments rather, for things like pile driving or offshore construction, surveying work, Navy ship shock trials. We've done that as well. Maritime domain awareness, you want to know who is where doing what. For example, IUU fishing, people fishing illegally, that's illegal, unregulated, undocumented fishing. Fishing vessels sound very different when they have their fishing gear deployed. They're often straining if they're towing a net. They have their hydraulics on. It's very easy. It's a fingerprint. The defense and homeland security applications, this is where most of the acousticians at AOS have cut our teeth in the defense world. And we built an instrument that is applicable to most of those missions. Environmental inversions, I included that because Kevin and myself, that's what we do. And so, I like to say that, I'm not just the CTO, I'm also a customer. We built the device that we wanted for all of our work, and doing environmental inversions like measuring sediment properties and ocean properties with the sound is what we've actually been using the instrument for. And then finally, oceanographic and meteorological observations. And I'll talk about a few of those right now. So if you're not into to math or the specific science we're working on, the details of what was done here isn't necessarily the takeaway. The takeaway is that we are using these instruments today to do the science that we want to do. So this is a case study that I'm taking credit for that Kevin did, where using single hydrophones, he was able to invert for sediment properties using nothing but ambient noise. So there was an experiment we helped with that a lot of other really great organizations were involved with, called ADION, where there was landers deployed on the seafloor, and we towed sensors as well. And by essentially modeling what the ambient noise would be from all the ships in the area, the wind, and other sources of natural noise, and then adjusting sediment properties until the ambient noise, shown here over time, matched up with the observed ambient noise, we were able to invert for large swaths of the ocean sediment properties using, like I said, single hydrophone observations, which is an innovation and nothing but ambient noise, so no anthropogenic noise in the water. So this is one of the use cases that we did. This is another one. So this is using acoustics to measure rainfall. So for a lot of the folks who are doing maritime robotics or sensing platforms, rainfall can be a bit of a tricky one because all the usual rain gauges like you have in the weather station at your house don't love rocking back and forth. And so, yeah, there are a lot of really cool optical and, ultrasonic sensors out there. This is an alternative to those. So essentially rain makes a sound, unsurprisingly, and that sound is a function of both the rate of rain as well as, the type of precipitation, big drops, little drops, et cetera. And so there's historical studies that show that, basically what rain sounds like. And then by, processing data from, again, single hydrophones and looking at this is frequency on the x-axis here and, noise level on the y-axis, essentially, again, by matching what we're seeing there's a lot of guess and check in acoustics, if you haven't been picking up on that. But by matching the observations, with the modeled noise levels, you can estimate what both, the binary distribution of yes, it's raining, as well as rates of rainfall. We are intending, although it's not implemented today, to include this as one of the vanilla examples of a capability on the Borealis that you get with any spotter buoy as an example of what you can do with the data. So testing. We wouldn't want to launch a product now 17 minutes ago without having a whole bunch of data in the water. I think my engineers say you need at least a month cumulative data before they'll ever tell somebody that something works, and we're getting there between all the various tests that we've done. I'll show examples from 2 experiments that were done using multiple Borealis units, one that was done by Applied Ocean Sciences in Long Island Sound, using 2 new and 1 slightly used spotter buoy there, and then one that was done here by the SOFAR team to show you, an example of how you could deploy and process the data off these instruments, as well as, examples of the instruments working. And again, they're only getting better as we continue to iterate on them. So in this particular experiment, there's 3 of the Borealis units, exactly like the one you're passing around, with the SQ17 hydrophones. There's also a unit with 2 Aquarian AS1 hydrophones to look at the difference between different piezos, as well as this Cetacean Research micro radar controller. Cetacean Research is awesome company that does acoustic recorders. It's something that we used a lot before, so we wanted to see how our instruments compared to something that we were very familiar with. So in this particular deployment, Julian, who you'll see wandering around here, and I got in the mighty warship AOS research vessel there and deployed 3 buoys in Fisher's Island Sound, in Long Island Sound there. So this is where we were. We deployed the buoys over here. They drifted over here. We did a lot of controlled source work, as well as various patterns with the small boat to do some detection, localization, things like that. These are the 3 buoys afterwards. They did come back. They were waterproof. And they did record data for the entire time. So in that binary measure, it was a successful mission. Just showing here the deployment, because these are easily deployable, handleable by a single person in a very small vessel. These are some examples of the acoustic data that was recorded during that experiment. It actually looks a lot better today than it did then because we've swapped out some components because we're never fully satisfied. But this is darn decent acoustic data. On the left hand here, we have an acoustic test sequence that I like to use. Now, if you're a huge acoustics nerd, you might actually know what this pattern is by looking at it. It's for Elise. It's do 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 do. I just use it because it's got a lot of really good frequency content. And like, if you've ever done an acoustic experiment and had to listen to that ping for days and days and days, you'll know that like mixing it up is actually, nice. So these are some controlled signals we did just to test the actual response at a variety of frequencies. And this is another one of those sort of beautiful CPAs of a vessel when our small boat passed the recording instrument. Like I said, after we tested it and were becoming satisfied with the results, we sent a few units here to SOFAR. They deployed it as well. You can see where they did it on the map. Their mounting was a little nicer than ours, and this is what comes with the instrument if you buy it from them. And so they mounted it right here, deployed it for, I think, multiple sort of one-day periods. And I think there's a couple of shorter deployments as well. When they deployed it on the spotter buoy, of course, that means everything streams back to the SOFAR's dashboard. These are the time series of wave height, current speed, all the usual things that the buoy is capable of measuring. And this is what the configuration looked like for the deployment, where you have the buoy, a drop line, and the hydrophone below. The drop line is generally designed to decouple the acoustic instrument from surface motion because the number one rule of sensing acoustics is that everything that can make noise will. And the number two rule is that everything that can't make noise also somehow will. So you got to do a lot of work to decouple it, and we've been working very hard with the SOFAR team to do that. The data is not necessarily great because this was the first deployment. The mooring's way quieter now than it was then. The acoustic data is cleaner. The reason I show this is that literally the very first time they put it in the water, we were detecting whales. So if your question is, can it detect whales? Yes, on accident, it can detect whales. If you're doing it on purpose, it will do a better job. So this is, how do you buy Borealis? Well, like I said, the product page went live a few minutes ago. And the price tag is $2,700. We actually kind of like announcing the price because A, it was really hard to get it down that low, but also if you've ever bought a lot of acoustic instruments normally, or oceanographic instruments in general, normally you have to get quotes and things like that. We kind of like just saying, everyone knows exactly how much this costs. This is how much it'll cost. You can buy it on the website today. It's live today. That being said, it won't show up until June because we just want to make sure that this is the first batch. That being said, this first batch, there are opportunities to purchase it through the accelerator program that we're a part of. The price will never be better than this. And if you buy it now, you get all of us in the SOFAR team obsessively supporting you to make sure that it meets your needs and you have a good experience. So if you're thinking about buying it, consider the pre-order option right now. This is what the website will look like if you go to it. It says pre-order now there for that price, and it will be delivered by June. If you have any questions, that's my contact info. And then general inquiries can be sent to the sales at Applied Ocean Sciences. That's also the support line if you have an instrument, and we'll get back to you right away. So with that, are there any questions? Yes.
Is it affected by fouling?
Can you ask that question to the microphone for our remote folks?
Thank you. Is your sensor affected by fouling?
Is it affected by fouling? Yes, ultimately, but much less quickly than optical sensors. Optical sensors are pretty sensitive to, a very thin film where you pretty much would need to be encrusted like at least multiple millimeters deep to probably centimeters deep before this instrument would really start caring about biofouling. That being said, given that it burns 40 milliwatts and the SOFAR spotter buoy can provide many times that, it could actually be that biofouling becomes the single biggest limitation on deployment length eventually. Yes, in the back there. Good luck throwing that.
All right.
Yeah, maybe like a team effort.
Just two quick questions. So one, does it support multiple channels on a single instrument? And two, it's mentioned a 60-day limit on the 1 terabyte SD card. If you're streaming over the spotter buoy, is that still a limit, or can you access the SD card to kind of clean data regularly?
Definitely. Yeah. So answer to the first question is all of the electronics inside can support 2 channels, but right now there's one phone hard affixed to it. So you would need to contact us and say, hey, I want a second phone on there, and we would do a custom job. The multi-channel system that can support up to 8, we hope to launch this year. And so actually everyone here hold me accountable to it. First of all, show up next year. Second of all, if we don't have a multi-channel system, everyone give me a hard time. So we hope to have an 8-channel system, very, very similar in form factor by this time next year on the market. Wait, what was the second question again?
The SD card, the 60-day limit, if it's connected to the spotter, is that still applicable?
So if you turn down the sample frequency, you'll extend it. So it's absolutely dependent on when it'll fill up, but it also won't break then. It'll just start overwriting the oldest data. So if you're streaming data out or getting reports, no, it will be limited by when the mooring breaks, it washes up on a beach somewhere, or it biofouls centimeters thick of stuff. Like those are the things that are going to limit its deployment size. We have sort of like a hard, fast rule at AOS that we never claim something we haven't done. And so we're confident we can get this thing in the water for over 2 months before it shows up on your doorstep in June. We've already had it in the water for multiple days. And so we're not going to be able to test it to years, but we intend to. Like we're going to drop a few as far out into the ocean as we can sometime this summer and monitor them for hopefully years or until they wash up on a beach. You can duty cycle the recording too. You can fire up the high-powered processor, the Raspberry Pi, and write a bunch of stuff to the second SD card if you really wanted to. So you can actually double that just by sacrificing some power efficiency. And like I said, you can not record all the time. You can turn it off, 5 minutes on, 10 minutes off, something like that. And then, like I said, we don't know how much it'll be limited, but we are so vastly below the amount of power that the spotter buoy can provide that it's limited by physical things that any deployment system would.
Wonderful. Thank you.
Thank you. Yeah, and Mike, you got a question?
I got a question.
Awesome.
You mentioned 8 channels. Can you configure that as a line array?
Yeah, so our plan is to have an option of the line array, which I'm hoping Niru's team will assemble for us because she's better at it than we are. And so a thin line toad array, kind of the garden hose style. Line array will be one option that we offer, and the other will be an expandable tetrahedral, or just 8 phones plugged in that you zip tie to whatever configuration you want. So those are sort of the 3 configurations we expect to launch with the recorder.
Perfect. Thank you.
This is actually a question for so far. What's the power availability in the Arctic?
So in the, hello.
Or high latitudes?
Yeah, so we have sustainability with default sampling configurations up to around 60 degrees. When you go higher than that and you want to last through winter, you have to start making choices around what do you want to reduce in duty cycling. But that is where we have the configurability where you can say, oh, I don't need as much wave data. I don't need to send reports as often. And so there is this kind of nice gradual degradation of coverage that we can support with the flexible knobs to tune in the power delivery.
That's great, thanks.
And that being said, Evan and I are obviously not satisfied with that. So we are also looking at, just giant packs of batteries that you can put in the spotter buoy for certain specialized applications like that, in which case, again, with 40 milliwatts, it will be measured in years, not days. And we had a question up here as well, I think. Oh, there we go.
I have this stuff.
Oh, your question's going to be hard.
Hey, Chris. Nice to meet you and nice to see finally the product. As you know, I work in acoustics. But question is about the 40 milliwatts. That's just the hydrophone, right? I mean, if you start to do edge computing in the Raspberry Pi, then you need a little bit more or not?
Yeah, so it is the hydrophone, it is writing, and it is doing all of the decade band noise level analysis, and it is doing an energy detector, all in the 40 milliwatts. If you wanted to run classifiers and stuff like that, so for example, for those of you guys who don't know, these guys make awesome AI-enabled acoustic processors. We need to fire up the Raspberry Pi for that. Low end of that consumption will be 400 milliwatts. High end will be 700, because we've at least done some tuning, that you can do in the, the standard Pi ecosystems to shut off the stuff we don't need.
When can we start testing it in the deep waters of Azores?
Julian, when are you going to get him his beta unit?
I'm already waiting for so much time. I'm impatient. That's why I fly all the way from
He
Europe.
flew all the way here just to make sure we couldn't get away.
And if
so-
I don't leave with one of those things, I will be mad with you.
we're planning on doing a lot of deployments of their software on our hardware, and we are a month and a half behind schedule on our end, not yours. Soon, very soon, we'll get you the beta unit.
Yeah, I think we can help you with testing in very harsh conditions and stuff like that. So that's why
We want you to break it
yeah,
as
more or
much
less.
as possible.
Yeah. But I think at this time, that's what you want, right?
Exactly. Yeah.
Yeah.
Yeah. No. So we're looking for beta customers who are going to break it. We're looking for people who do really exceptionally hard and challenging things with acoustics, who will use it, who will break it, who will make Julian's life a living hell, and then we will make it better. And the product will continue to improve. Julian, raise your hand so he can spot you. Don't try to
That's why
hide.
the guys. Yeah.
So he's the one you gotta.
Hey, it's
twist his
awesome.
arm.
Thank you very much for showing this.
Thanks again.
Yeah.
We got time for one more.
Can I? I wanted to do.
Right. Part of my questions were answered, actually. I was wondering what type of edge processing you were running, but you mentioned energy detections and others. I just thought about, if I had multiple of these, instead of having 8 hydrophones on a string, can I start timestamping measurements from every single one? And how accurate?
My God,
Do I need another clock on
I
board?
can't believe I forgot to talk about. So you're like a plant, because that's the thing I'm most excited about doing with these. So we have an experiment next month where we're going to be deploying 3 of these for the ostensible purpose of just ambient noise measurements, and we're going to be testing exactly how well we can do the semi-coherent processing across multiple platforms to do triangulation. Right now, we get the GPS from the SOFAR spotter buoy. So we do have GPS time. We are meticulous about the synchronization and tracking the time in the metadata of the file system. And so it's going to end up depending on how close they are, right? As you get your units further apart, the coherence is less, but it's more forgiving to a couple of milliseconds. I think it's going to be successful on the first try, and so because we are being so careful with the timing to make sure we can do it. We haven't. Actually, no, we have tested with that Connecticut experiment in post without doing any extra alignment work. I was able to do triangulation, good cross correlations across the buoys that were agreeing with the GPS tracks. So yeah, we can time sync them well enough to do coherent processing. If you put them really close together and need ridiculous precision, then you should also get a beta unit and break it, and then we'll make it even better. But yeah, that's definitely part of the goal.
Thanks.
Thank you.